Value. This is a concept which, if I mention the word value, what do you guys think of?
The theory of value.
A theory of value. I think you've all been through marginal product, the neoclassical theory of value, and that sort of thing. Now, when you think about what financialisation is talking about, that's prospects saying that the financial sector, which is not seen as one of the inputs to production, okay, taking more and more of surplus over time. But the question that's left out of that is what surplus in the first place? Okay? What do we mean by surplus? So I'm going right back and saying, how do we produce more outputs than inputs? Okay? Now, that's a question that economics should actually start with, in my opinion. That's why I'm starting here. Because if you look at the universe itself, there's an answer to that question. But none of the theories of economics actually start from what the engineers and scientists have taught us about the nature of the universe. So each school's got its own particular answer, and it also defines value in its own self-referential way. And that's where a lot of the confusion comes when you see different schools of thought on the very few occasions actually do argue with each other, and on the frequent occasions that the other schools criticise the neoclassical, they're actually assuming different definitions of value without even saying what they are half the time. I'm including thermodynamics. I'm starting from that point of view because that's to get the correct answer about what is value and what is surplus, you've got to be consistent with that law. Now, that doesn't mean you derive economics from thermodynamics. There was a Georgescu erosion, in some ways attempted to do that. I'm not saying you derive it all from that level, but I'm saying if what you have isn't consistent with that, you're wrong. Simply as simple as that. And that therefore means that every existing theory of value in economics is wrong. Okay? Not just the neoclassical, the Marxian and the post-Keynesian as well, in that sense, are wrong. The question is whether you can actually revive any of them. So to be correct, if you have a theory about where production comes from or where value comes from, where surplus comes from, that is not consistent with those laws, you are simply wrong. Now, ironically, when you take a look through the history of economic thought, which is one of my areas of interest, the only school of economics that ever really got close to it was really the first thing you could call the school of economics, and that's the physiocrats. Now, has anybody heard of the physiocrats before? You have a bit. Have you read any? Have you read any of the physiocrats, or?
Well, a lot of history of economic thought was to start with his name, so.
Close to Kinney, yeah. How do you pronounce his name? Kinney. My God, my French is dreadful. Like my hearing is awful and my French is worse. So Kinney.
I think so. I'm not French, so I don't know.
Any French experts in the room? No. Okay. Yes. Q-U-E-S-N-A-Y. U-E-S-N-A-Y. Huh?
And you say his name will know who
Yeah. It's Kinney. So I'm fairly close. I say Kinney. I go, but Kinney. Kinney. Okay. Well, he was the leading personality. I'll actually check up. I'm sure on the web I can find a pronunciation system. I'll give that a try and see what it says to me. But they were the only ones that are even close to being correct. Now, what I didn't mention in the title is the third concept of dialectics. And who's read any Marx here?
We have to.
You have to. Okay. Okay. Yeah. Well, there's a dispute amongst Marxists as to whether Marx actually derived his economics from dialectics or not. There's a particular interpretation that says don't read Marx on philosophy. Ignore all that dialectic stuff. I think that's totally wrong. I think if you don't understand dialectics, and most Marxists don't, you don't understand Marx. So I start from that because I think from that foundation you can build that theory of everything in economics that neoclassicals thought they had, and history has proven they haven't, as well as the logical flaws they've ignored. That I will put forward to you in the second lecture that you can build a theory that fits all this together, but it contradicts what most Marxists believe, including contradicting the labour theory of value, which makes me very popular with Marxists, even more so than I am with neoclassicals. So that's the organising principle behind the approach I take to economics, and I'm going to take you through that after I get through the stuff on value. And there'll be quite a lot of detail because, again, a lot of Marxists will, again, they cherry pick what they like in Marx It's like you can cherry pick the Bible if you belong to a particular religious sect or whatever religious book you care to do. And I've been through everything Marx ever wrote in economics, and I want to show the background for all that. But today I'm talking about value. And if you look at the Neoclassicals and the Austrians, their definition of value is subjective. Okay? It's the idea that value is what, when you talk about society promoting value or increasing value, what they talk about is increasing satisfaction of the consumer. That's what they're really talking about. So the utilitarian view of what value is. Value is the satisfaction we all get out of consumption, ultimately. That's the sort of definition they have. And you can find, again, because Neoclassicals tend to forget where they come from, they don't study the history of economic thought. You won't find a lot of discussion of that in textbook. Let's take it for granted and keep on going from that point. But I think the best overall view of this is put by Jean-Baptiste Say. Have you heard of him? Say's law, etc., etc. And this was his proposition coming out of what he called a catechism on political economy, which I recommend reading just to get an idea of this particular philosophy and I think Say's underknown role in generating that philosophy. And here he's having this little discussion with he's written the catechism is a discussion between himself and somebody else where he's pretending to be both characters asking himself questions, and the ignorant person is answered by the wise Say. And in this he says, what is value? And his answer is, give to anything to a material that has no utility, you give it value. So increasing the utility of something is increasing value. And value itself is seen as utility. That's pretty much the neoclassical perspective. The post-Keynesian school, and again, largely I'm identified with the post-Keynesian school, but there are people in post-Keynesian who like to kick me out. I make a few arguments there. But in general, that's the school I feel most at home with. And in general, their reaction to the disputes that existed between the neoclassicals and the Marxians back in the late 19th century, when you had all these controversies between the classical school, which Marx represented at that time, and the neoclassical school, which was coming out in reaction to Marx largely, the post-Keynesians basically looked at it and said, we don't want anything to do with that. There's such a war, such an unproductive war, they think, well, output just grows. Yeah? They have theories about where production comes from. Obviously, they've got models of production, but they pretty much just accept that it's growing, and they don't really have a particular theory of value. So there's a particular paper by actually a good friend and guy who marked my PhD thesis decades ago, Jeffrey Harcourt, and a co-author, Hamuda, and that's called Horses for Courses, basically saying neoclassical post-Keynesians are agnostic about what is the source of value. They're agnostic about an intellectual foundation. They don't want a general theory of everything. Let's just use the most appropriate model. Now, in fact, one of the best comebacks of that was written by a guy called Bacchus comes to mind. And his argument was, if Horses for Courses applies, why do post-Keynesians refuse to hop on any neoclassical horse? So, in other words, there's something inconsistent. If you're a critic, almost always a critic of the neoclassicals, would you say, let's be agnostic about our foundation, and why do you reject the neoclassical foundation all the time? Which I think is a fairly reasonable, Roger Backhouse, that was the author, a fairly reasonable argument. Now, the classicals, if you go back to the classical school, if you start with Adam Smith, and most people do start, hi there, no worries, most people do start with Adam Smith as the foundation of the classical school, then the definition that Smith had was fundamentally value is embodied effort. It's what's required to produce something. In other words, rather than being a consumer point of view on value, it's a producer form of value. And he also argued that labour is dominant, but not the only form of effort. Now, there's lots of, the whole labour theory of value is incredibly fraught with misinterpretations of other writers. But if you read Smith at one stage in The Wealth of Nations, you'll see him talking about that he argues that a farmer is more productive than an industrialist. And part of his reason is, he said, even their labouring cattle are labouring, effectively labour for them. So he was seeing rather than saying all the effort comes from human work, which is what Marx ultimately tried to reduce labour theory of value to, Smith actually had the argument that animals on a farm contribute some value. So Smith was not as rigid on the labour theory of value as Marx was. But fundamentally he said labour is a dominant form of value in terms of effort that produces output, and increasing value involves increasing the division of labour. Now, if you look at Marx before 1857, he was much stricter about this and argued that value is embodied labour. And if you get any course by a strict Marxist, that's what they'll talk about as the foundation of value. And he saw the increase in the amount of value coming from further exploitation of labour. And I've got exploitation in inverted commas there because what Marx effectively said was that the fact that labour received its means of subsistence and then is exploited for capacity to work was just part of the law of capitalism. It wasn't a case of nasty exploitation. It's just the way capitalism is. That's why I've got it in inverted commas. And you'll find much more eloquent statements of that from Marx himself. But I'll leave that for next week because I'm going to go through and pull that apart as well. But what I'm starting from now is thermodynamics. Who's any engineers in the room? Good, I'm safe. Okay, because I've taught myself thermodynamics in a sense by knowing that we needed to bring that into economics. So have you all done humanities degrees?
Sorry?
Have you all done humanities degrees before coming here for the masters? Economics? Pardon?
Economics is humanities, yes.
Pardon?
Economics
yeah.
is humanities.
Yeah, okay. Well, what thermodynamics is, has anybody here just read any thermodynamics? Or am I starting from a blank canvas here? Pretty blank? All right. Okay. Pardon?
I know that I'm not going to read it formally.
Okay. There's a wonderful author called C.P. Snow who had the he's English, very unusual situation of being both a physicist, a leading physicist, and a novelist, writing back in the 1930s. And so he talked about the two cultures. Actually, if you look for that book, you'll find it on the web. I recommend downloading it and having a read. It's a very literary work by somebody who knows science as well. And he said he was in the unusual situation of having, during the day, he'd work with engineers and physicists, and in the evening he'd go out with writers and playwrights and actors. And he said there are two completely separate cultures. And what he find at night when talking with his friends from the theatre is they thought those scientists were so ignorant. I mean, how many of them have read The Merchant of Venice, for example? And Snow at the same time would say, how many of you understand the laws of thermodynamics? Okay. Now, they couldn't, why do we need to know that? Well, he said, if you don't understand that, you don't understand the real world in which you live. Okay. So I want to take you through that in a very general way, what they're called the laws of thermodynamics. Now, you've all heard of things like the law of one price in neoclassical economics. Okay. Does it apply? Okay. How about the law of comparative advantage? Okay. Yeah. Does it apply? They're all garbage. Okay. All those so-called laws are totally violated. The laws of thermodynamics are undeniable. They've been so strongly confirmed by empirical evidence. If you deny them, you actually believe in perpetual motion machines. Now, there's various ways in which we're looking at generating energy out of various effects of quantum mechanics and so on. But in general, as was put very eloquently by another writer at much the same time as Snow, and he's a physicist who was probably as well known in his day as Stephen Hawking is today. So he wrote both. He was actually the guy who confirmed Einstein's general theory of relativity. You may know about what's called the transit of Venus. Okay. There's also when the sun moves, when we move around the sun, and therefore we see a star in the far distance, then the gravitation of the star, according to Einstein's theory, would bend the light. So if there was no bending effect going on, then as we moved around the sun, and that star in the distance, from our point of view, became closer and closer to the light coming from that star became closer and closer to the sun, then according to Newton, no effect, the light would come straight to us. Okay? According to Einstein, it would curve a bit. So after the sun had moved slightly in front of the star, we would still see the star. And I think the degree of bending of light was something like 0.18 or 0.09 of a degree of arc. And that was Eddington was the person who confirmed that by observation. So that's the seriousness of his role in physics in general. But when talking about and trying to popularise these laws for the general reader back in the 1930s, I think it was, 1920s, 1930s, he said that this law is the laws of thermodynamics are so true that anybody who thinks they have an argument that goes against it is simply wrong. So he said, if you look at somebody says they've got a set of their own set of equations in disagreement with Maxwell's equations about electromagnetics. Well, I said, well, so much for Maxwell. If you can find a theory that transcends Maxwell's possibly wrong. Great. All right. Said, if you found that it's contradicted by your theory is contradicted by observation, well, sometimes those, and he was an observational physicist. Okay. Sometimes the observations are made badly. They'll make a mistake. We've had history just recently of that. You would have heard about the time when physicists in England thought they'd found neutrinos travelling fast at the speed of light. Okay, that was an error. Okay, no, that was a mistake. There's another one apparently recently I've heard about. I don't remember what it was. Gravitational wave. It's a piece of dust, wasn't it? Yeah. Dust on the observation. Yeah, I know. So we haven't found gravitational wave. Even black.
They did.
Pardon?
The laser one afterwards.
Pardon?
They confirmed it with LIGO.
Oh, okay.
They confirmed it with that.
And the confirmation was wrong.
Yeah. Well, no, they confirmed it. They thought they confirmed it with, but then it was the dust. And then there's LIGO, which is this massive laser beam that they shoot.
Yeah.
And that caught two black holes merging, so it created a.
So it did actually find it.
Yeah, well, two different experiments.
Okay. So in this case, again, what Eden is saying here is, well, sometimes they get it wrong observation, they'll correct it at a later stage. Your theory might still be right. But he said, if your theory contradicts the second law of thermodynamics, I can give you no hope. There is nothing for it to do but collapse in deepest humiliation. Okay? Now, that is the state of all economics. Fundamentally, the current theories of production we have, including post-Keynesian, not just neoclassical, definitely Marxian as well, violate that law. So let's take a look at a bit of a background of the laws themselves. And why was it that economists didn't make their theory consistent with the laws of thermodynamics? Well, there's one good reason. Most of the economics we developed using even today was developed before those laws became solid amongst physicists themselves. And if you look at what economists tend to do, when they think they're aping physics, and Phil Murawski writes a lot about this. You heard of Phil Murawski? Okay. Worth reading. Very hard to speak. Phil swallowed a dictionary written by Thorstein Veblen. So he uses incredibly complicated language. But it's very much worth reading on these points and many others. But economists tend to use physics 20 or 30 years out of date when they start using it. So if you look at what was done by the early Neoclassicals to try to develop what they saw as a mathematical equivalent to physics in economics, they were using physics pretty much from the 1840s to 1850s when they were writing the 1870s. And Phil's way of characterising that particular approach to physics was what he called energetics. It was before this set of laws were found, before the irreversibility processes were proven as well, and before the necessity of waste was proven. Imagine if you had theories of economics developed where we accepted you could not minimise waste. You could not eliminate waste. Okay? Would you have a theory of perfect competition? Okay? If you realised you could not eliminate waste? Probably not. I hope not anyway. So that's one reason why the economic theories themselves haven't incorporated this, but they've had a century and a half to get there and they still haven't done it. So you have this absence of a relationship between the two. So what you find is economists will give you models of production, models of the ecology even, which aren't grounded in these unbreakable laws. So they're producing models which violate those laws, often without even knowing they're doing it. And my favourite starting point is the so-called circular flow diagram. You would have seen numerous examples of that. And that effectively, most of them, the vast majority, treat the economy in complete isolation from the environment. Okay? Imagine the economy can operate with nothing coming in to the system that isn't produced in the economy itself. Okay? So here's some examples. I think this is from Mankiw. And it has, notice it's got product markets, firms, households, factors of production. Try to find anything about the ecology there. Okay? Nothing, all right? There's a woman called Kate Raworth. Have you heard her name? Okay, Raworth, Kate Raworth. Kate's, I keep on forgetting the university she had. I think it's Oxford, not in the economics department. But Kate has what you call the donut model of capitalism. She's trying very hard to popularise that, and part of it is critiquing this whole notion that you can have production without any input from the outside world. This is another one. Same story. Government, financial institutions, product markets, firms, household factor markets. Nothing about stuff coming in from the environment externally into the economy, and nothing from the economy affecting the environment itself. So there's no non-economic input or output in those models. Everything's been produced by the economy itself, and everything's consumed within the economy. Now that is fundamentally wrong. That implies that is effectively saying the economy is a closed system which generates output and uses everything, and nothing produced in the economy goes anywhere else. Now a closed system cannot produce anything over time. A closed system, in fact, necessarily degrades. So this is also implying there's no waste going on. Okay? That's a great starting point for economists, isn't it? One reason why a lot of economists are climate change deniers, or certainly supported the climate change denial movement. So it's a huge environmental blind spot. When you look at it in a genuine sense, the only reason we can produce anything is we're exploiting energy, even England. I believe the UV index today is 0. Okay, but there's still some sunlight coming in here. So everything we're using, solar energy, fossil fuels, nuclear energy, that was stuff that existed before humanity. Okay? And in fact, humanity only exists because that stuff exists in the first place. We cannot produce energy. That's the first law of thermodynamics. The energy that exists in the universe just exists. It changes its form, okay? But the amount of it, we can't produce energy. Now, I'll give I've got a lot of personal anecdotes from all the exposure I've had to economists over the decades. And once I was giving a presentation at the United Nations Environment Program. Okay? So you'd think the economists inside there would know something about these laws. And I was working with a guy who is a physicist by background, and we were talking away about the role of energy in production. He said, if we don't have enough energy, we can make some more using labour and capital. And we both just froze, and so I sort of thought I might as well break the ice. And I said, so you believe in perpetual motion machines, do you? And he went, what? And I said, mate, you cannot make energy. It's one of the laws of thermodynamics. You cannot produce more coal by combining labour and capital. You can mine existing coal using it, but you can't produce it. Okay? So that's the first law. So we can only exploit the energy that currently exists. And that includes converting matter into energy. That again obeys the laws of thermodynamics in that sense, that the matter's equivalently converted into energy. So, and then when we're exploiting that energy, we're necessarily generating waste. So we can minimise waste. We cannot eliminate it. And again, this is something engineers learn very early on in their own education. So again, this is something where economists, as a particular version of humanities, are incredibly ignorant compared to engineers, who they'll often deride as not understanding how society functions. The second and third laws show you can't produce without generating waste. So if you're going to modify the circular diagram to make it a bit more realistic, realistic in the very first place, not something which is subject to Eddington's complete rejection, but at least realistic enough to be roughly used, what you have to say is that, first of all, the energy inputs have to be there. They've got to be coming in from outside the economy. They can be exploited by the economy. They are not made by the economy. And then unless they're there, you can't produce anything at all. And there's waste going back into the environment as well. So you've got to have something roughly looking like this. There's the sun, or a lump of coal, which of course is fossilised solar power, or, it's a lump of uranium there, pardon me, got it wrong. Okay, so the sun or fossil energy we've stored, which is stored solar power, or nuclear waste, which is stored power from supernova explosions and so on, giving us a flow of free energy, which we then use to generate useful work, okay, which then turns the system around. Some of it necessarily being wasted. We simply can't take advantage of that energy in the first place. And I've also omitted, I should have included it there, waste from the environment from the economy going back into the environment as well. Yeah.
Well, waste in this context is that we can't convert 100% of energy.
Yeah, that's right.
Waste in this context would not be CO2.
That's right. I've left that out. That's my mistake. So I'll add that into the diagram in a couple when I get back home. So that's at least the essential thing, is you can't exploit all the energy that's available. But we also generate waste itself, which you dump back into the environment. So why can't we produce without using already existing energy? And why can't we produce without using waste? Well, it comes down to these laws of thermodynamics. As I said, empirically, absolutely true. Yeah? There's never been an example of them being violated. If you have a theory that violates them, it's the theory that's wrong, not the laws themselves. Very, very different to what economists call laws. And they were discovered in the late 19th century, which is after Marx developed labour theory of value. Marx effectively accepted that in 1844 and became fairly rigid about its meaning in 1847, I think. And the Neoclassicals were developing in the 1870s, but the physics they knew was 1840s, 1850s. So they were basically ignorant about this particular area when they put their own theories together. So that consequently meant that these rules and the mathematics behind them in particular was never part of economics, was never part of the foundation. And the maths is complicated. So I find the best way to convey it to people who aren't doing an engineering degree is a joke. And the joke is this. It says, this is the joke law of the version of the Laws of Thermodynamics, which C.P. Snow developed to try to explain it to his colleagues. Okay. 1, you can't win. Good start for a set of laws, isn't it? 2, you can't break even. And 3, you can't leave the game. Okay? Not exactly the usual cheery economics argument about maximising utility, is it? So slightly more informatively, you can't win, you can only break even. You're in a game where all the best you can do is break even. Okay? You can only break even if you can find somewhere in the universe that's absolute zero. The third law, there's no such place. Okay? We've actually managed to generate some experiments where a set of photons or a set of fundamental particles have been hit by lasers so that they've been slowed down to the stage where their temperature, which is largely a measure of movement, is a tiny fraction above absolute zero. Like between 0.00001 degrees Kelvin above absolute zero. But if we try to dump anything into that, the whole reason it's done is we isolate that from the rest of the universe completely, using power to do it. If we tried to dump anything into that, we'd eliminate the experiment completely. It'd be gone. So there's no huge spot where you can dump waste where the temperature is zero. So just to translate that, first of all, saying you can neither create nor destroy energy. Okay? You can transform its form, because when that solar energy comes in here as high frequency light, it goes back as infrared when it's reflected back into the universe, and that's where it bumps into carbon atoms, which gives carbon dioxide atoms, which gives us our problems about greenhouse effects. So energy can neither be created nor destroyed. You can just change its form. The maximum amount of energy you can use is limited by the background temperature in which you're trying to use it. That's the second law fundamentally. And only if the background temperature is zero can you use all of that available energy. That's why you're right about saying I'm just leaving out the waste we generate internally. It's the energy we can't exploit that I'm talking about here. So only if the background temperature where we're working is absolute zero can we use 100% of the available energy.
Well,
yeah.
I would have a slight objection because, of course, you can not transfer all energy into work, but for our human purposes, I would argue we can use a lot of the energy because all the waste energy in the end will be heat. So if we do energy heat kind of combination, we can push it up quite far.
Let's say I've got an object in this room which is at a temperature of 23 degrees. Yeah. Okay, how much of the energy now can I use to do work? What's the temperature of this room? I'd say it's roughly 23 degrees, wouldn't you? Yeah. Okay, can I use that heat source to generate work? No, that's my point. Yeah. Okay. So that's the final point. The only way to exploit all the energy, we'd have to find somewhere in this room which is minus 273.15 degrees Kelvin. Okay, roughly 300 degrees Celsius below the temperature of this room. Okay, and big enough to dump all the energy we're generating out of whatever energy source. There ain't no such place. So that's the basic laws to say you simply can't generate without waste. You've got to waste some of the energy you're trying to exploit. Okay, this is the basic reason why it's inevitable. What you've got initially is potential energy. If you were standing if you had a window there, and you decided to step out the window, potential energy is how much force you can implement on the ground once you fall the 4 or so stories down. That's potential energy. So I went looking for ages trying to find an instance of potential energy. This is the only example I could find where there's water falling over a waterfall and the buggers had locked the wheel. So the wheel's not turning, okay? But of course, if they opened up this sluice gate, you can see there'd be water coming out over the wheel as well, and that would be spinning. If anybody can find me such an illustration, please send it my way. Okay, that's the basic idea. You can only turn the wheel because the waterfall's higher than the spot it's falling into. That's the potential energy you're trying to exploit. So there has to be a gap to be actually use energy in the first place. And the same thing applies in general. The maximum you can extract from an energy source depends upon the gap between the energy itself and where you're dumping it. If there's no gap, you can't exploit the energy. So that's only possible because that waterfall is more than 0 meters tall. And the same applies in general. You can do work using an energy source if the energy inside the source is greater than the energy of its surroundings. But then what you end up doing, of course, is the energy below that is still generated but can't be used by you. So think about a heat pump. And this was the ultimate proof of this was done again in the 19th century by a guy called Carnot. And of course, I've totally stuffed the pronunciation. It's another French name, Carnot. But Carnot proved the fact that there had to be waste even in the world's most efficient energy exploiting engine, and he designed it. It's called a heat engine. So what this does is simply take heat from a source, dump it in a sink, and then works out how much of that energy you can actually exploit. He designed the idea of an ideal piston, which is you'll find actually heat engines you can even buy in some shops with illustrations of Carnot's principle. So imagine you've got an engine which is burning oil and is running at a temperature therefore of 500 degrees Celsius. And the environment, say it's 25 degrees Celsius, a nice warm summer's day in London. Well, there's going to be a flow of heat. And then because of that flow of heat, you can use that flow of heat to harness the energy difference. Okay? But that means the maximum amount of energy you can generate out of that is 475 degrees Celsius. And of course, the actual temperature, when you put it in Kelvin, which is what's the temperature above absolute zero, add another 273 degrees on top of that of energy you're effectively wasting. So in that case, the efficiency of that engine is going to be about 70%. But if you have an engine, say, 500 degrees Celsius, and you happen to be on Venus, where the average temperature is 500 degrees Celsius, there's no flow of heat, nothing to exploit in the first place. All you'd be doing is making the engine as hot as the surroundings. So you can't harness the energy. That's the basic reason you're going to have to waste some of the energy you're using. Now, it isn't just a question of how powerful the energy is, which you measure by the heat that it can generate. It's how cold the surroundings are. The basic idea, you've got the heat of a source, which is hotter than the heat of where you're dumping the source. The terms engineers often use as source and sink, or when they want to differentiate, let as source and dump. So that's the maximum amount of usable energy that's going to be there. So none of this, of course, involves the point you made earlier about our own creation of additional waste in the environment. A large reason why I don't talk about that, by the way, is because I get a few climate change deniers in classes, and I don't even want to go there. So it says this: even if there was no trapping of heat by the biosphere whatsoever, this still applies. Okay. So the maximum we can get out of a source of energy depends how cold the surroundings can be, and the coldest surrounding temperature is absolute zero, which is minus 273 degrees Celsius. Now, some physicists would like us to use that as our reference point. Okay. So we're actually saying the temperature in London today is roughly 285 degrees. Okay, that'd be a realistic measure of temperature as opposed to what we use. We use the melting point of water as our reference point. Pardon?
Still better than Fahrenheit.
Yeah. Okay, so there's nowhere in the universe that's cold. That's the third law. So the average temperature of the universe, even in the vacuum of space, the average temperature there is about 2.73 degrees Kelvin. So even if we moved our production to outer space, which frankly I think we have to do because of the biosphere issues ultimately, and we've got to getting the technology to get there. It's probably in your lifetime we'll see the first examples of producing output in outer space. If Elon Musk gets his way, and even Bozo from Amazon's trying a similar thing. So, but even if they do it up there, they'll get much more energy that they can actually make use of, but they'll still have the limit of 2.7 degrees worth of it that's going to be wasted. So the average temperature of the Earth is roughly 16 degrees, so 292 degrees above absolute zero. So energy source we use here, we're going to be wasting that much available energy. Or the same production process in outer space would use the additional 289 degrees, but not 292 degrees worth. So that much energy can't be harnessed on the Earth. And at least that much potential energy is wasted by any energy extraction service we're using on the Earth, even if we've got none of the issues of producing waste, which of course we do, and none of the issues of trapping that energy, which of course we have. And again, a lot of climate change deniers don't seem to appreciate that if we didn't have global warming, the temperature of the planet would be about minus 20 degrees Celsius. So that's, given the amount of radiation falling on the Earth from the sun, that's what roughly the temperature of the rock we're in would be about 250 degrees above zero. So even an ideal engine, which has no friction, no leakages, etc., is going to waste some energy. Its maximum energy has to be less than 100%. So you have now working in terms of source and dump, which is to get the different letters there, called the source S and the dump D. Then the maximum amount of work W that can be done is 1 minus D divided by S. Now, if your dump is running at, say, 300 degrees Kelvin, which is a hot summer's day in England, and the source is 1,000 degrees Kelvin, which would be an incredibly good car engine, then your maximum efficiency is 70%. Not 100%. Now, I really would like to see what would happen to economic theory if economists fundamentally understood that when they developed their theories. That's why I said the idea of perfect competition. Would they have thought of the possibility of it being feasible to talk about an economic system which is 100% efficient in avoiding any waste as economists define waste? I certainly hope not. So perfect efficiency is impossible. 30% is wasted even with an ideal engine, and the actual waste is going to be much higher most of the time. And that's the good stuff. That's the part where we said you can't break even. Okay. Now, the even worse stuff is the tendency in normal is for when you exchange heat with an external system, which you have to do, otherwise you can't extract the energy. If it's a closed system, it will degrade over time to a uniform temperature. So the level of order in the system will degrade over time. The second law is one of the hardest laws to get your head around, and it's also one of the hardest ones to express in. There's always going to be an objection from an engineer about how I define it, which is going to be justified. I'm just stuck with that, unless I sit down and really take myself through a full course on thermodynamics, and even then somebody's going to say I get something wrong, I'm sure. But power generation itself, doing useful work using energy, works because we're dumping waste heat into the environment. If we don't do that, we can't extract the energy. So definitely, therefore, that's where the type you're talking about. What's your name, by the way? Benedict. I'm going to try to slowly. I've got. Oh God. I'll go back. I'll try later. No, maybe during the second session. So to actually exploit it, we have to generate that waste. That's unavoidable. So imagine you've got. This is a typical example from an engineering textbook of the basics of generating energy from a boiler. So you've got a boiler where you're boiling water using coal or gas or oil, whatever else, maybe even nuclear power. And what they're showing, you can see we won't say it's an engineering example because there are actually numbers on it. I don't have any idea what P. I presume that's pressure equals 1 atmosphere, 101.32 kilopascals. That's my guess. Okay? And then they've got different temperatures. Temperature of the circulating tub is 25 degrees. Temperature over here is 25. Probably it's megapascals. So they're talking about the pressure of the pump coming in and so on. So it's all for an engineering textbook. This is much more detail than an economist would ever give you. But the fundamental point here is that notice there's both whoops, hang on. I clicked on the explanation here. So we see often when I've got an image like that, I'll link through to the background explanation for it. So when you're looking at my slides, and I'll give them to you through Study Space, as much as I hate the bloody software, that'll take you to, if you click on that image, it'll take you to the background there. Okay. But what I've got there, that's generating power, but it only generates power because you're dumping the waste heat here. If you didn't dump, that's another word. That's why cooling towers are essential. You see them all over the landscape. You know? If they weren't there, there'd be no heat coming out of it as well. I have heard some not particularly well-informed environmentalists saying, if only we get rid of the waste tower. Sorry, get rid of the waste tower. You don't get any energy out of it. Now, if that was completely isolated, If you didn't have the waste tower, you couldn't get any energy out of it either, for a simple reason. When you think about it, the temperature of the entire system would become the same. Okay? If you had a totally closed system with no dumping of the heat, then ultimately, roughly speaking, there'd be some waste, there'd be some variations from where the boiler itself was to somewhere else in the system and so on. But fundamentally, the temperature, if the same, and the turbine wouldn't spin in the first place. Okay, it's got to spin to get the energy out of it. And that applies in general. A closed and an isolated system goes from high order to uniform order over time. And therefore, when it's in uniform order, you can't take any energy out of it. You've got to dump it in something else. So, and this is, again, one of the terms I find really quite confusing. I always get it wrong. Not always, but most of the time. What we would call a very organized system, they call low entropy. What we call a very disorganized system, they call high entropy. So if you have a highly ordered system, it has low entropy. If a very disordered system, it's got high entropy. And that's, again, I keep on getting mucked up with it. I'm sure it's one of those things like accounting terms of credit and debit that confuses engineering students when they first start. So if you imagine you had a piston in a cylinder, which had pressured all the air, most of the air to one side of it, and most of the rest of the side was a vacuum, that's low entropy. It's very organized. Most of the stuff's in one spot. Now, if you look at that piston slide over time, then this is going to happen. So the pressure on either side of the piston is going to be much the same. So you've now gone from low entropy, which is very organized, to high entropy, which is disorganized in the sense that the pressure is the same either side of the system. And that's a universal tendency. Okay? Unless you have some external energy source coming in, that's going to happen to any particular system. And there's always a good cartoon to illustrate this sort of stuff. So here's a little girl or boy explaining, Mum, it's a mess because of the second law of thermodynamics. Okay? You've got to put work in to stop the place getting from a state of order to a state of disorder. So that's the basic background we have to say, how do we actually explain where surplus and production comes from? And that's now to start moving on to the economics. Pretty close to the hour. I might just take a bit of a break there and then come back and I'll go on to the economics. Two key things come out of all this. One is that you can reduce waste. And there's plenty of potential still to reduce the waste we generate in production, but you can't avoid it. Okay, it's unavoidable. That's in terms of using available energy. Okay, there's even additional in terms of the amount of waste we generate through the production process itself. So in that sense, you've got to have economics and ecology linked. If you can't do it, you haven't got a decent theory of economics. And unfortunately, that's still the case. So we don't yet have a decent theory of economics. Great starting point, isn't it? And that's even with environmental economics, because even though a lot of work has been done and a lot of journals exist and a lot of good researchers are there, it's still not to the stage where you can say ecological economics is ready to take over from neoclassical economics. The second thing is that energy is essential for production to occur at all, but production apparently goes in the opposite direction, because you go from less order, we take raw materials and turn them into finished products. Okay? So what's actually going on there? We take this disordered stuff and we turn it into ordered stuff, and we end up with each time more ordered stuff than we had beforehand. Okay? So the second law is unbreakable. What's going on there? Well, production has to increase disorder overall while it creates products. Okay? You simply can't avoid that. That, again, is one of the laws of thermodynamics. So even though we talk about producing output and we want to minimize waste, etc., we can't get away from the fact that in using that energy, we are increasing aggregate disorder. There's actually quite a few arguments I've seen in evolutionary biology and so on to argue that what life really is a mechanism for achieving the second law of thermodynamics more rapidly. Okay? If life didn't exist, we wouldn't have as much waste being generated. We're actually speeding up the process rather than slowing it down. We just tend to count the outputs and not the inputs. So we go back to this key question about value and a surplus. When you ask the question, how do growing economies produce more outputs than inputs, you have to have an answer that's consistent with the second law of thermodynamics. So how do you produce it? Well, how can you have outputs exceeding inputs and being more ordered than those inputs as well over time? You can't get that from an isolated system. If the economy is like the model of the circular flow, there'd be no output. Okay, so you'd have the degradation of the output system rather than the increase in quantity of outputs and quality of outputs. So production is only possible because the Earth is an open system. We've got energy coming in from the outside from the sun, and we've got stored energy as solar energy, and we've also got stored cosmic energy if you think about explosions of supernovas, which generate the heavy elements that we can then split using nuclear technology. Only because we've got that energy there can we exploit that. And then farms and factories exploit this to produce more outputs than inputs when we measure it in terms of the ordered elements. Okay, more outputs in terms of iPhones than inputs in terms of silica, but we necessarily create more disorder in doing it. So if you added up the total of what's being produced, you'd necessarily have a negative. Okay? So the idea that you can actually price the waste to eliminate it, sorry, you simply can't do it. So the disorder of outputs exceeds the order. Okay. That makes a bit of a change. Do you think you can now use a price system to control global warming? You know, if you priced all the waste, you wouldn't be able to make a profit. Okay. So we have to make huge revisions of what we believe in economics to make it consistent with those laws of thermodynamics, even if we're not trying to derive economics itself from thermodynamics, and I don't believe we should. It is an emergent layer of behaviour, but we have to be consistent with that foundation. So long as we remain on the planet, economics and the ecology are necessarily linked. Production necessarily requires energy, and labour and capital can't produce energy themselves. They can mine what exists, okay, but they can't produce it themselves. And they can't be substituted for energy either. You might change the technology that's used to exploit the available energy. You might improve the energy efficiency, but you can never make it 100%, and you can never completely replace the energy with the labour. And you can't produce the energy either. And my little insight that led me get to the next thing I'm going to show you, because this is new research which I'm still writing up and still developing the empirical work for with a good friend from the Bank of England, Michael Kumoff, and a few others. This was this little insight. When you think of how we describe production, we've talked about producing output using labour and capital. And then when people have attempted to build a model of production involving energy, what they've done is simply added energy in as if it's something like labour and like capital. But the whole idea that labour and capital can exist without energy is nonsense. And this is the insight that got me into realising it. Labour without energy is a corpse. Okay? If I could find one of you in the room with no energy, you'd be dead. Okay? And capital without energy is a sculpture, which reminds me, I forgot to turn that camera on. Hang on. No energy going into to try and see if we can record the second part. Era 305. I don't think I can. At least we'll see how the first one goes down anyway. So that little insight, I mean, it's nonsense to talk about labour and capital independent of energy. Okay? What you can see them as is means to exploit the energy which exists. That applies to us as well, even if we're thinking in a hunting and gathering environment. We exist because we exploit plants and animals that we find that already absorb some of this energy themselves, and we then use our own energy to capture them. And in doing it, if we don't take enough energy to keep ourselves alive, we die. So we've got to have that energy surplus above what's necessary to survive to be able to capture additional energy in the first place. So you require three types of inputs. You've got energy from the open system of the planet itself, which is either direct or solar or nuclear. Labour, which has its own energy embodied in it. If it didn't, it couldn't actually do any of this. And machinery, which also embodies energy. So a factory has an energy store itself, and it's using energy to actually turn the wheels that enable it to exploit the additional energy that's taken in. So you have, and then think about what production does. What does production do? Well, it produces three types of outputs. There's useful work. If you think about what we call GDP, again, that's a term that economists always just say, here's GDP. It's a number, you know. Let's use index numbers to convert it from nominal to real, etc., etc. But what the hell is it? Now, again, ecological economists have done a lot of talking about that, and one of my colleagues in that area says that economics is the only so-called discipline, which adds up the assets and liabilities and calls that the total of something, rather than subtracting the liabilities from the assets to get what your equity is. But fundamentally, if you really want to think about what GDP should be measuring, it's useful work. It's something that does something we want done. Okay? So useful work might be recording a video or recording a talk or moving from, as I've done, from Waterloo to Surbiton. Okay? It's useful work. Having a car accident is not useful work. We should be doing those subtractions. But generally speaking, let's think about, imagine a system where we were just producing useful stuff. Then useful work is the definition of GDP. We're transforming matter into useful products or services. Whether that's food we eat, transportation we take advantage of, entertainment, it's useful work. It must also produce waste energy. So there's energy, and that's the main thing I've focused on so far. Because of the laws of thermodynamics, some of that can't be reduced. It's unavoidable. We can reduce it. We can't eliminate it. There's also waste products, and that's the point you made, Benedict made earlier. In reducing these outputs, we produce little things like cyanide. Okay, carbon dioxide is the obvious waste product we're focusing upon right now. But that's the main thing. Where by exploiting fossil fuels, we're necessarily generating carbon dioxide, because all those fossil fuels are carbon compounds. And now we can reduce the waste in terms of production itself. If you think about when you make something like this mouse I'm holding right now, to make the things itself, pieces of metal had to be cut and thrown away. Okay, 3D printing, you might be able to make it without actually having those elements of waste. So you can minimize the tooling, but you still have some irreducible waste. Still going to be unavoidable. So when you want to visualize this, the rough way of doing it, the economy is an activity inside the biosphere. And again, this is getting the status right. A lot of economists think they can fix the economy using economics. They fix biology, the ecology using economic ideas. That's got the whole thing back to front. That's treating the environment as a component of the economy. It ain't. Sorry, the economy is a component of the ecology, not vice versa. If you think you can fix the bigger system using what's going on inside the smaller one, you're going to make a mistake. So we have the economy as an activity occurring within a biosphere. We produce a surplus because we're harnessing that free energy. And those are the various forms of free energy. That useful work powers the economy itself. We use labour and capital to harness that energy, and that's producing useful work. We necessarily generate waste, which is both physical and energy waste, and they're due to both the necessities of the laws of thermodynamics and also the inefficiencies we could reduce by improving the state of technology. But we simply can't get away from it in the total. So we're dumping that back in the biosphere. And that's generating that waste that we ourselves produce. And then the biosphere itself has to cope with it. And, of course, given the scale of human activity now, we're just adding that small little bit that's necessary to make the system unstable. So we have a slowing down of the transmission of that waste energy into outer space, and that's what's giving us global warming and all the other phenomena we're seeing. If you take any look at the state of the environment these days whatsoever, we're affecting the biosphere. So, of course, that can do as well. And if you want to model this properly, you have to then say, well, if this happens, you're undermining your capacity to produce in the first place. And those are the things we still haven't got properly incorporated in any form of economics, though the environmental movement is a lot further on. So what I want to do now is say, can we make economics consistent with those laws of thermodynamics? Now, looking at the various schools of economics, if the Neoclassicals made themselves consistent with the laws of thermodynamics, they would no longer be neoclassical. They'd transform their nature. Because, first of all, what they're seeing as a source of surplus is this increase in utility. I've got a lot of arguments as to why this is, which is not the right foundation to start from. I think that's a subjective perspective on value theory. I think we have to start from an objective one. They don't explain how that's possible. And what they're saying is production, in their models of production, they say output is a function of technology, labour and capital. They don't have any explicit role for energy. So if you think of the Cobb-Douglas production function, have you had that in any of you've done it in your previous economics, and yeah, I can see Richard giving a grimace about it, justifiably so, but I'll show you what you can do with that later. But this is basically saying that output is some constant, some term A, which reflects the state of technology, times labour raised to one power and capital raised to another, where the sum of the powers is 1, which is basically saying if you double all inputs in equal proportion, you'll double output. So constant returns to scale. Now, there's no explicit role for energy in that. And what it implies, and I've given you an example where, a guy with a PhD in economics working for the United Nations Environment Program, literally, without being conscious of it, obviously, argued that the energy is just another form of capital. We can make it if we need to. You can make machines, you can't yet make people, and you can never make energy. So, capital is manufactured. By definition, that's what a machine is. It's a machine. It's a material thing we have made. You can't manufacture energy. And when you look at their model of production, it's really the mirror image of their model of consumption. Consumption, they have commodities can be substituted to generate utility. What they have in their theory of production is that the same argument, that inputs can be easily substituted to produce outputs. Now, that is not true. It is simply not possible for the substitutability they presume for consumption, which itself has got serious problems. And I'll talk about, if I teach a course in history of economic thought, I talk about that. You'll also find that in debunking economics. But you cannot easily substitute those inputs, and you certainly can't substitute capital and labour for energy. You can more efficiently use the energy you're exploiting, but you cannot substitute. Now, it also imagines, and I've mentioned this point a few times, it imagines the idea of perfect efficiency. They talk about perfect information, perfect composition, perfect this, all kind of cases in which there is no waste going on. Now, if they were truly conscious of the laws of thermodynamics, then surely the economy, which is a subset of physics, would equally be subject to its own principles of waste. So the whole idea that you can eliminate waste, get perfect efficiency, is an obsession that I don't think economists would have if they properly understood the laws of thermodynamics. But the real problem, and I'll talk a bit about this, not enough yet because I still haven't done enough work on the concept I'm going to show you myself yet, but the theory of income distribution they have no longer works, because what they do is they link the income of the labour and capital to marginal productivity. So what they're saying is the wage you get paid reflects your contribution to production. The profit that capitalists earn reflects the contribution of the machinery the capitalists own to production. And therefore there's an inherent fairness in their theory of distribution. You can't complain about it, it's just you get your marginal product. And also they have incomes completely accounting for the output. Now, when you say energy is not manufactured, who pays a lump of coal? Somebody pays a worker, somebody pays a capitalist, nobody pays the lump of coal. We pay the person who owns the lump of coal or owns the machine that actually burns it. But the actual energy is an essential input to production, which is not paid. And if we tried to pay it, we'd lose money because of the laws of thermodynamics. Okay? So what we're doing is we're exploiting that energy source, and then we're sharing in a fairly conflictual way the benefits of that between the social classes that are involved in production. So labour and capital can't account for all output, and the prices can't match marginal products. I've still got to go through the technical proof of all that stuff, but that's what I'm going to show you with a set of equations to actually include energy in an essential way. So in that sense, the neoclassical perspective on capitalism fails when you properly include the laws of thermodynamics. You don't need to go through all the other things that are wrong with neoclassical theory. It's just once you realise it that much, it's no longer neoclassical theory. Now, different schools of thought. Well, as I said, only the physiocrats, Quenet and Cantillon and Turgot and so on, were actually consistent with it, because they actually asked them the question, how do we produce more outputs than inputs? Okay. And that's the essential question. And it dates back to Francois Quenet. I've got to change my pronunciation. I'll check Quenet. Okay. Who was a doctor for the King of France. At the time, they'd started to discover arteries and veins in bodies, because before this body was sacrosanct, you couldn't cut it open. Now, in the experimental, the post-Renaissance period, people were actually saying, let's carve open a body and see what it consists of. And they were amazed to find Well, they knew to some extent from looking at your own body there are these blue things which we can see, which are the veins, as we now know, veins, okay, close to the surface of the skin. You don't find arteries that, well, you do actually, small arteries, you do find them. But they then realised there are all these cables and something of fluids being pumped around the body. So this is why we call it the physiocratic school, because a physiologist, a physiocrat, was the first one to say, well, maybe the economy is the same sort of thing. Circulation is necessary. So that was a major insight coming from Kane. But they had the idea of circulation of money and goods flowing in different directions around the body and being essential for output. But they also made the argument that surplus only arises in agriculture. Now, again, think about the time they were writing. This predates Smith. Smith actually went over to France and tutored a child in France to payment to learn, so he could go and learn from the physiocrats at the time. And in my opinion, Smith completely stuffed up, because the most important stuff the physiocrats had he didn't bring across into what became classical economics. But the logic they had to say that surplus was only something coming out of agriculture is that agriculture is the only industry that receives the free gift of nature, which of course at the time they were writing was overwhelmingly the sun. We weren't using coal to a large degree. We had some furnaces. Of course, we made iron. We didn't make steel at the time. We made iron. Okay, that was the Iron Age. Steel Age only after we produced the Bessemer processes and so on later in the 18th century. But back then, obviously we had furnaces to make iron. Hi. No worries. It's a bad time of morning to start a master's course. But what you find is so it's overwhelmingly agricultural society as well. France was much more agricultural, much less industrial than England was at the time. So looking at the world, what they saw was the agriculture was receiving the sun, and the sun means that a farmer can plant one seed and harvest 1,000 seeds, effectively. So the surplus is obvious in agriculture, and that's why they saw it. And this is, I think this is Turgot's explanation. The husbandman, by which they mean the farmer, is the only one whose industry produces more than the wages of his labour. Okay? He therefore is the source of all wealth. Okay? The soil pays him immediately the price of his toil. Now, this is often derided by economists. I think how primitive this is to say agriculture is they were the only ones to get it right. Within the context of what they knew at the time, they were the only ones to get this right. So nature, what she grants, is a physical consequence of the fertility of the soil. And the soil's not fertile without the sun as well. Okay, what they saw is plant a seed in the ground, and 1,000 seeds are grown by that one seed. So the physical surplus is there. It's obvious in agriculture. But fundamentally, they're still seeing producing this free gift. That's the essential of why you can produce a surplus. So they actually predate thermodynamics by a century. You're looking at roughly 1760, actually even earlier than that with Cantillon. So land is the source of matter from which all wealth is drawn. Man's labour provides the form for its production, and wealth itself is nothing but the food, conveniences and pleasures of life. Okay? 1755. Predates Smith and wiser than Smith. Ironically, I'll show you shortly a phrase from Smith where he's clearly read Cantillon and liked the phrase. He used the phrase without the wisdom. So what they saw with production required the free gift of the earth. And that's what I've been pretty much arguing to you in more modern terms in the previous lecture. Without that, there's no production, and yet our theory of production in economics doesn't include it except for the physiocrats. So this is again, there's a beautiful clarity to the way the physiocrats write. So actually a lot of modern French writers can learn something from that, including what's his name, the guy who wrote Capital, Piketty. The French academics have got into obscure writing these days as a style. You read the original writers in French and they're brilliantly clear. The produce of the land divides into two parts. The one is the subsistence and profits of the husbandman, the reward for his labour. So that's actually paying the wages of the worker. Okay, and that's saying there's not just subsistence, there's a certain bounty as well. You're paid more than your subsistence as a farm labourer. You can go off and get drunk on mead or wine in France, obviously. So there's more than just subsistence in this vision. Again, compare that to Marx, talking mainly about workers getting subsistence. It's saying there's a bit of pleasure as well. The other, which remains, is the independent disposable part, which the earth produces as a free gift to the proprietor. So what they're seeing here is the source of profit is that the proprietor can exploit that free energy. And that's true. That's a hell of a lot wiser than anything produced in an economic sense. So this is the way Kane represented what's possible. It's called the tableau economic, and again, I'm sure I'm mispronouncing that. Tableau? Tableau? Tableau. 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 Oh, actually, I'm close to being correct. What a shock. Okay. You can actually download it on the web. It's very hard to see it here. That's the original handwritten version. Actually, probably not handwritten. That would have been done as a lithographic print, I imagine. What he's got on the left-hand column is what he calls the output to productive on the left-hand side, which is agriculture. On the right hand, he's got sterile, which is manufacturing. And the middle, he's got revenue, which is the king. Okay, so agriculture is a productive sector. That's that bit there. Manufacturing is sterile. So because there was no obvious case where you plant a piece of steel and you get 10 pieces of steel coming out of it, it wasn't as obvious that there was actually a surplus being generated in industry as well, because it's exploiting the energy of coal and wood and so on at the time. So it was seen as agriculture captures that free energy and then exploits. We know that industry actually exploits stored energy as well. We know that now. That wasn't known back then. And then the fundamental insight they made, given that they didn't know about nuclear power and they didn't really have much exposure to industry and the fact that we're using energy in industry, their fundamental insight is correct. To produce a net product, you must be harnessing a source of free energy. And what they saw is effectively the workers get part of that as a wage, which includes a bit of a chance to have some fun. Okay. But you'll fight over that, which is what led to the French Revolution. But the surplus that the owner gets is the remainder. Okay. And that's, to them, the sun was the ultimate source of that. So that question, unfortunately, has degraded over time. Value should be that ultimate question. The physicrats were the only ones to really ask the right question. What the neoclassicals come down to saying is how a price is set, relative value. Classicals are what's the source of profit. So only these pre-classicals got the question right. How do you produce a physical surplus? How do we transform inputs into outputs, where the outputs are greater than the inputs in both quantity and quality? Okay. And now we talk in terms of entropy and so on. So this is a little link to a Monty Python Inquisition saying, pardon me. Some of my things aren't necessarily serious. So how do you produce more outputs and inputs? Well, the physiocratic answer was you exploit the free energy from the sun. So agriculture is the productive sector, and others simply transform what agriculture has produced. That's why they call it the sterile system. So it's wrong, but within the context of the time they wrote at, it's the correct insight to draw and the correct question to ask in the first place. So they divided society into three classes, what they call the productive class, which is largely agricultural workers, and they were productive because they were the ones who exploited that free energy. So you've got this person working in a cornfield, planting seeds of corn, and the surplus is easily seen because you put one seed in, there's your corn seed, down comes some heat from the energy, up comes multiple ears of corn with maybe 1,000 bits of corn for the one corn you put in. So the surplus is physically obvious in that situation. That's why they could see it. But they actually, in contrast to Smith, they did see it. Smith didn't make that link. So the sterile class was the industrial workers because they take that agricultural value and then transform it. And the final class was the proprietors, the owners, and they got the remainder. Okay? Above and beyond what was necessary to pay the wages of the agricultural workers who turned corn into more corn, and the wages of the industrial workers who turned that corn into carriages, which is the main term that in the tableau economic, that's what Kine, it sounds like I'm using my own bloody name, doesn't it? Kine used as the example of industrial output. So they're wrong about agriculture being the only one exploiting that free gift because we use coal and nuclear power now, but they wrote before it was actually possible to see that in the country that wasn't doing it on the scale that it didn't begin with Watt's steam engine, but England was, because it was using coal a lot more at that stage, though without on the industrial scale we now know, England should have seen the possibility. And what should have happened with Smith is say, well, you're right about agriculture, but there's also this stuff we're doing in industry. Now, that wasn't done. So, again, repeating myself a bit here, we're harnessing that free energy to increase order within the economy while decreasing it overall within the ecology. So that insight was lost as you went from Smith, from the physiocrats to Smith, where they started talking about labour and the division of labour. So if you look at Turgot, he's saying here, and again, I think it's quoting again, it is out of the share of the proprietors, what's called the revenue, that he can live without labour, and he can carry wherever he will. So he really saw capitalists as living off the surplus above what they paid to workers, which was coming from the free gift of nature. So wrong about being a free gift, but correct that the free gift is essential. Now Smith, on the other hand, has a switch from land to labour as the source of value. And here you have Smith starting off by saying something which is obviously taken from Turgot. Remember that phrase I showed you earlier. Every man is rich or poor according to the degree in which he can afford to enjoy the necessaries, conveniences, and amusements of human life. Very, very similar to what Cantillon wrote before him. But then he says, but after the division of labour has thoroughly taken part, only a very small part comes from your own labour. Most of it derives from the labour of other people. So we're shifting from seeing land and exploiting free energy to labour. The whole idea of, well, how does labour manage to have the capacity to do that work disappears. And then he says the value of any commodity is equal to the quantity of labour which it enables them to purchase or command. So we're drifting now from an acknowledgement of free energy as the source of surplus to seeing labour as the source of surplus. And he finally says labour is the real measure of the exchangeable value of all commodities. Now, it would have been possible to say energy was, and some people still argue for that. I don't go quite that far. But what you've now lost is that link with producing a physical surplus requiring free energy. Instead, they're saying the physical surplus is now seen as coming from labour alone, which is where Marx turns up. So Marx says that labour is the source of all surplus. He says the worker received means of subsistence in exchange for labour power, but the capitalist receives, by paying the subsistence wage to the worker, gets the productive activity of the worker, the capacity for the worker to replace not just what he consumes, but give to the accumulated labour a greater value than it previously possessed. In other words, Marx is now saying it's the difference between subsistence for workers and the work that workers can do is the source of surplus. Again, ignoring the energy completely at this point. Now, what you saw with the Neoclassicals, again, because Marx used this as a critique of capitalism and an argument for socialism, the Neoclassicals ended up ranking no input above any other in terms of its importance. They said, no, both labour and capital are necessary, but they ignored the whole issue of where did surplus come from in the first place. They had no real clear concept of surplus. They talk about, consumer surplus and producer surplus in terms of this efficiency of their model of the firm, but they're not talking about the physical surplus of goods being produced, and they're not talking about any role for energy. And what the post-Keynesians have done is just reject the substitutability argument, not completely, but fairly heavily. They're saying that you always use labour and capital in fixed proportions. So they're rejecting the substitutability, but they haven't got a role for energy inside there in any explicit sense. So the only correct answer about what is value, the source of value is free. And I don't mean it doesn't cost any money to buy coal, but I mean it pre-exists. It wasn't created by anybody. It's just there already. So production is a process that takes that free energy and takes matter, which is a low entropy, the very disorganized form like iron ore, and produces very highly refined stuff, but equally more waste. And if you look at the total level of disorder, it's greater from the product than it was from the inputs. So the waste, when you add up everything produced, there's more disorder coming out of production than beforehand. Otherwise, you're trying to deny an undeniable law. And Bob Ayres, by the way, is both a good friend and a major physicist who's been working in this area physicist stroke economist. So back in 1969, he invented the term externalities. So that's a link to that original paper. So what you see for labour and capital is they're necessary to produce output, but they can't produce output without energy, and they can't exist themselves without energy. So we have to find a way of incorporating them. So you can't exploit the free energy without them, but they can't exist themselves without that free energy. So can you incorporate energy in an essential way into production functions? That's something I've been wondering about for a long, long time, and I dreamt this up last year, and I've now had enough feedback to know that nobody else has done it before, and enough feedback to say it's correct in a logical sense, but I've still got to then look at all the implications of it. But yes, you can make energy an essential element of production simply by saying, well, there's an absence of energy in all existing theories, but it's possible to bring it in. And I'll show you this trick. So if you look at the labour theory of value, that's seeing surpluses being derived from and proportional to labour input. Neoclassicals say the substitutable factors of production. Output is a term representing the state of technology at time t times labour to one power times capital to another. Post-Keynesians basically use the argument, and I do in all my modelling at the moment, of arguing that output is either proportional to capital input or proportional to labour. Now, the first attempt, not the first attempt, but probably the most sophisticated attempt to date to bring energy in was developed by Kummer, Linares and Vordonis, and that's called the Linux function. Linear exponential is what the reason for the term, and that says that you've got the factors of production include energy. So if you put it in what's called a Cobb-Douglas CDE form, as they call it, they use other ways of showing it as well, but that's basically saying that output involves capital raised to the power of alpha times labour raised to the power of beta times energy to the power of 1 minus alpha minus beta. So fundamentally, it's just adding energy in there. Now, I've been working with Bob for about 3 years now, and I was never happy with the fact that you use this form, because all you've got to do is make sure that alpha and beta sum to 1 and energy becomes 0. Okay? It's not there in an essential form in that equation. And that would still argue you can get output with 0 energy, which is wrong. And that, of course, implies that they can function without energy, which is also wrong. So that was my little corpse and sculpture moment. And I thought the whole idea of saying you can have labour and capital without energy is nonsense. So what you have to do is rethink it to say that let's now use labour and capital, or represent them as means to harness free energy. And how much of that free energy can we actually exploit? And think of GDP as useful work. So what you then see is GDP itself is a function of energy, and output is a function of capital and labour, both using energy together. It's simply saying that that's incredibly simple when you look at it. In fact, what embarrasses me about this stuff is I thought I'd come up with a really complicated equation. And what I got was bloody simple. And to me, the embarrassing thought was, surely I'm not the first person to think this up. So I spent some time checking the literature, and others did too, and apparently I am the first. But let's go through it. The actual work done by capital and labour, first of all, depends upon how many units you have of both. Now, obviously, it's easy to measure unskilled labour, just the number of hours at work of people, that doesn't involve any skill that they can't be taught on a production line. Machines is much harder. That's where you get the whole issue of have you heard of the capital controversies? Okay, that's because you're going to Kingston. Okay, other universities, you wouldn't hear about it if you did to be told the Neoclassicals won it, which is crap. But that's, thank God, you're not getting that nonsense here. So Engelbert would have taught you something differently, and so would Devram and Rex and so on. But I'm going to, for a while, gloss over that and imagine I can work out the number of machines involved. And you can also think about this down at the level of micro-industry, but I'll be working at the aggregate level. But imagine you can, for the meantime, talk in number of units of labour and number of units of machinery. Then what you've got is the flow of energy that the units of labour and units of capital can exploit per unit of time. So if you think about yourselves, roughly speaking, if you're actually working as unskilled labourers, probably the maximum amount of energy you could consume in a day would be about 4,000 calories, and maybe half of that you could devote to work, 2,000 calories. So that's the sort of units of energy per unit of time that I'm thinking about here. Now, when you think about yourselves, if you're going to go and work as an unskilled labourer, you can give a certain amount of calories of energy to the manufacturing process. But of the calories you eat, some of them have to stay in you or you're going to starve. Okay? If you eat 4,000 calories, you cannot do 4,000 calories worth of work that day, unless you're trying to lose weight. Okay? So to maintain yourself at your current weight, probably half the calories you consume are going to stay inside you. So only half the energy you consume is available for useful work by your employer. So that's the first little link there. And then the efficiency with which you do that is the other issue. Imagine what I was trying to do is to move a weight from here from this wall to that wall in 1 second. Now, the strict definition of what I'm talking about for efficiency here is simply working out the mathematics of if I wanted to propel a 1 kilogram weight from this wall to 10 metres away in 1 second, I'd need to impart a certain amount of kinetic energy here to start it and a certain amount of kinetic energy to stop it before it hits the wall. Okay? So that's the ultimate definition of efficiency. Okay? Now, we're going to be less, if I carried the weight, then I'm going to be less efficient than that process. The amount of energy I use to move from here to that wall is energy that not only moves with a 1 kilo weight, but it moves me as well. Okay? But if I did it on that's absolute, just sheer unskilled labour making the effort. Now, if I, of course, make that same move and I'm on a skateboard, then I use a lot less energy, but I'm using less energy because the machine, which we've manufactured, is making it more efficient for me to do that. So that's the type of definition of efficiency I'm talking about there. So what I've done here is say, let's take a look now at this function. So useful work as a function of energy is going to be a function of the number of machines times the amount of energy that machine can process in a given time unit. Let's say talk in terms of energy per year at the moment. Okay, but we actually have data on that. That's what I'm going to get towards. So there's the number of machines times the energy that a machine can throughput in a year times the ratio of available energy the machine can actually contribute to the energy needed to keep the machine going. Or that's total energy there. This is the amount of total energy which is actually available. Now, if you think again about yourselves, I'll talk about, I should have started with labour first of all there. Well, let's talk in terms of labour, and then you can apply the same logic to capital. So number of unskilled workers, the amount of energy that each unskilled worker consumes in a year, which might be, say, 4,000 calories times 365 days, the ratio of the available energy to the actual energy, which might be 2,000 divided by 4,000, so that'll be 0.5, and the efficiency with which that's done. Now, if you think about me, like literally walking from one side of the room to the other, let's say I weighed 99 kilos, the way I'm going at the moment, I'm probably going to get there, unfortunately, and I moved to 1 kilo weight, then I'm using 100 kilos, 10 metres to move 1 kilo. So my efficiency 0.01 at best. Okay, so that's the way to think about that number. Same sort of thing for capital. Assuming for the moment we can actually define the number of machines, and in fact I think I'm going to make that a simpler process over time. Number of machines, energy per year, available energy to total energy multiplied by efficiency. Okay, those are your two components. So now what I've done now, I've reduced this efficiency ratio to X for K for capital and X for L for labour. So that's going to be, say, 0.5 for you guys, maybe 0.7 for a highly efficient machine, 0.1 otherwise. And the efficiency with which the work is done, the example I gave a moment ago, walking across the room, that would be 0.01. Okay. The efficiency over here of a machine, well, it's got to, obviously the machines, until we get to robots, has to be included with the human to be activated. So let's put this now in the terms the Neoclassicals started with, which saying that labour and capital together multiply each other's impact. And if you think about the skateboard example, if I wanted to go from this side of the room to the other on a skateboard, clearly the skateboard's multiplying the efficiency of me making one push rather than having to walk all the way. So it's a multiplicative relationship. That makes sense. So now I've whacked these, again, presuming constant returns to scale. We might find they're non-constant. This is the basic source of changes in returns to scale comes down to the size of the machine you're working with. Because if you imagine like a blast furnace, the bigger a blast furnace gets to be, the area increases as the square of the, because you're talking about the area of the cylinder, but the volume it can be processed is increasing in a cubic fashion. And only when you go to do so much to control the interactions do you get any diseconomies of scale. That's what you mean by economies of scale. But if you mean like taking one 100 cubic metre blast furnace and reproducing another 100 cubic metre blast furnace, then it makes sense to say there's constant returns to scale. And if you imagine you've got industries which have worked out what is the ideal scale to work at, then again, constant returns to scale aren't a bad assumption. But that's the expression. Now, of course, I've got K here raised to the alpha and L here raised to the 1 minus alpha, which are exactly the terms you get in the Cobb-Douglas production function. But I've also got these energy terms that weren't there as part of the Cobb-Douglas production function. So I can rearrange it to grab out the Cobb-Douglas production function bit. And what you've got is what the Neoclassicals have been using, capital raised to 1 power times labour to 1 minus that power. But rather than multiplied by this abstract technology term, A at T, I've now got the energy used by labour and its efficiency and its available energy ratio raised to a power times the energy throughput for a machine raised to the same power as for the machine, okay? Not a different power. So looking at the components, there's your Cobb-Douglas production function. That's the energy parameters for labour. Now, if you think about them, again, we've talked a bit about this already, the energy per worker per day might be 4,000 calories. The efficiency might be 0.5. I'm using 0.5 again. So the available ratio of 2,000 to 4,000 is 0.5. The efficiency, I'm saying, it's 0.5. It's obviously a lot lower than that for unskilled labour. But that's roughly a constant. That's not going to change. And if you do change it, you get a maximum level and that's it. You can't go beyond that maximum level. If you had people being produced as slaves, maybe you might raise these XL 0.7. Give them a smaller amount, enough for them to stay alive, and the rest is available as energy for the slave owner. You might get efficiency to a maximum. You're not going to get past it being a constant, and it's just raised to a power. And so if you wondered what does that number work out to be, well, depending on the value of the power, it's somewhere between 500 if you're working with the value of the component of 0.1 and up to 0 if you have a value of 1. Now, for the machinery, the energy parameters for capital are very conceptually the same, but actually very different. The energy consumption per machine per day or per machine per year has risen astronomically, quite literally over time, because we're talking about going from the days of the Watt engine to the Falcon 9, okay, which Elon Musk is convinced can establish a colony on Mars. You think about the amount of energy used by a Watt steam engine over a year. You compare that to the amount of energy you could put through a Falcon 9 rocket if you ran it for a year, which you wouldn't need to do to get to Mars. Okay, huge increase. That's actually a Trumpism. Huge increase in the amount of energy that you're exploiting. That's where our wealth has come from. Now, XK, that's the amount of available energy to the energy in total. There's no empirical calculation of what that is. Okay? And it would involve working out what machinery is and so on. But clearly it's below 1. That's, again, the laws of thermodynamics mean that's the case. And the efficiency, again, that's well below 1, but we've done better at raising it over time. We'll probably keep on doing it. I think things like 3D printing and so on to produce goods and services are going to drastically increase the efficiency of doing things like stacking rocks on top of each other, which is otherwise known as building a house, and a whole range of activities like that, raised to another power. Now, the powers are no longer relevant to income distribution. I haven't worked that out yet, but I'm sure that's the case. So what you get is a formula that looks like this. That's taking out the energy contribution of labour, times labour raised to some power. Then you've got capital raised to a power times these energy components raised to the same power. Now, if you try to eliminate the energy, that's a constant. Okay. If you tried to eliminate the energy contribution of machinery, then you eliminate machinery as well and say output's produced with labour, and you're back in hunting and gathering without spears, without knives. Okay. If you try to reduce the labour, well, same story. You actually can reduce the labour, pardon me. If we get to the stage where technology is good enough to mean that we have robots doing all the unskilled labour stuff at the moment, that could be eliminated and still produce output. You'd have output being some function of the machines, which are the robots, times the amount of energy the robots put through over time. Look at the Cobb-Douglas production function. This bit is what the Cobb-Douglas production fits. It's just got A there, it doesn't specify it. But there's what's called the Solow residual. Have you heard of that? Okay. When Robert Solow, an interesting person actually, Solow is now becoming more and more non-neoclassical. He was a major both builder of neoclassical growth theory and was a warrior in the capital controversies on the neoclassical side, and apparently with good reason. He virtually hated Joan Robinson. I think really, if you see this on the web, he's really telling me what he actually thought about it. I'm sure I've exaggerated. But the battle between Robinson and him was a huge defining part of the Cambridge controversy battles over the definition of capital back in the 1960s. And Solow invented the second form of neoclassical growth theory, which became the basis of the first form of growth theory, became the basis for DSGE models, which the neoclassical now realising is a waste of time. So Solow's been on that side for a long, long time. But he also worked on this equation and tried to empirically fit the Cobb-Douglas production function, this one, to the data to find out what was the contribution of labour and capital. And what he found was 85% of the contribution came down to the A term. Okay? So it's called the Solow residual. Now, in any other discipline, it'd be called a huge mistake. Because if you make an equation for something and it only explains 15% of what you got, you've got a big hole in your theory. If you look at what's going on with astronomy right now and physics, that's driven by the problem that we now look at the amount of matter we can see in the universe, and we now believe that matter only explains 15% of what we see. So they've got their own residual. It's called the dark energy, dark matter problem. That's what's trying to explain that is what's driving astronomy today. Economists go this on, there's a Solow residual, let's keep on using the function anyway. Okay. Now what I've done in effect by bringing up this equation is that this is explaining, I think, and I think we'll prove it empirically over the next year or so, explaining the Solow residual as the contribution of energy to production. Okay. So if you look at the Kuhn-Millers form as I showed you beforehand, what my equation has, this one up here, is one less degree of freedom, because here this has got alpha and beta. I've only got alpha up here. You can get rid of the beta. In that sense, it's a more rigid, a more tied down theory. It's going to be harder to fit it to the data because there are less degrees of freedom. But what you can't do with the Kuhn-Millers form is you can't put this in output per worker form. Because with the Kuhn-Millers thing, if you divide through by labour, then you're going to have labour to the beta divided by L. So you're going to have labour to the beta minus 1. You can't get it in terms of a capital labour ratio. But if I divide through my function, because it has just the one term, you divide output per head, so that's GDP per head. Okay? It then becomes the constant representing the energy contribution for labour times the capital labour ratio, which you can't get out of the Kimmel form, times the energy contribution. And you can also relate this to useful work by machines per head by, let's divide through by L in general. Again, this is brand new stuff. I'm still working out the implications. I only worked out this particular one before giving a conference paper in Manchester at the Evolutionary Political Economy Association last October or November. But if you divide through by L, I'm now saying, well, output per worker is, actually I've taken the L down to the bottom here. And now what I've got is alpha as a scaling factor. And what I can do, I can get rid of K. Now K is the problematic term. We can't actually define the number of units of capital. But one thing we empirically do know is how much energy is consumed in manufacturing. We've got good data, kept by the Department of Energy, of course, of the energy consumption per year by industry. So I'm going to substitute that sum of total energy used by machinery. And of course, we know that's not including energy we consume to stay alive, but we don't eat coal. Okay? So our energy consumption as humans is separate to that. But I can substitute the total energy usage for K times number of machines times energy per machine. That's unknown. We don't actually know K. We don't know E to the K. We do know the product, the sum of the product. So I do that, and I now can say output is this constant representing labour's energy contribution times labour raised to 1 minus alpha times energy used in industry raised to the alpha times also those efficiency terms. So when you get that energy, that's my substituted equation now. So I'm now explaining output as being a function of labour and the energy harnessed by machinery. And you put it in per capita form, again you get some advantages out of this formulation. Pardon me jumping on the screen like that because this was done on the way for a conference presentation. I still haven't had time to update. So I'm now saying what's output per person? GDP per head, not even per worker. Well, I simply divide that whole expression through by n. And I can now group this. So now I've got n, here I've got number of humans, okay, over here with alpha, something raised to the power of alpha above it, and something over here raised to the power of 1 minus alpha. Now, one little trick, I learned mathematics from a brilliant mathematician in my first year undergraduate university, a guy called Williams at Sydney University. And he said there are 3 rules to mathematics. One is, what have you got that you don't want? Get rid of it. Second rule is, what haven't you got that you want? Put it in. Third rule is keep it balanced. Okay? So that's always in the back of my mind. And what I've got here, well, I actually want to get the employment rate. So I've got n here. If I take n to the 1 minus alpha, I can put it beneath that one. That leaves me with n to the alpha over here. Oh, I can then divide that over here. So this is now the employment rate, and this is energy per capita. We have data for those. So I now say GDP per capita, which is what y divided by n is this constant times the employment rate raised to 1 minus alpha times the energy per head we're using raised to the alpha times these 2 bits over here we don't know. Okay? But I've actually have data on that, and we have data on that, and I can get away with a while for just treating these as constants. So we have data for all that. Not this bit, but we have for those 2. So I've now got something I can empirically fit to real data. This is GDP per head. Now, it won't be, not that this is in America in 1960 per capita dollars. So GDP per capita in US in 1960 dollars, so adjusted for inflation. No surprise that it peaked at the financial crisis, fell, and it's now rising a bit in the recovery period. So that's the GDP per head data. The employment rate, this is actually not the unemployment rate upside down. This is why Donald Trump got elected. Okay. Now this is data taken from the Bureau of Labour Statistics. It's exactly the same source as data that you get the unemployment rate for. What the unemployment rate does is people go a survey, either the phone survey or knocking on doors, and they ask you a question, do you have a job? And you answer, if you're in Midwest America, no, I don't. I can't do the accent. Okay. And they say, have you looked for work in the last 2 weeks? No, I haven't. Oh, you're not unemployed then. Bye-bye. You're not in the workforce. Therefore, you're not counted as unemployed. And what the employment data says, knocks on a factory door and says, how many workers you got? I've got 1,000. Okay, thanks. Knock on the next factory door. So the employment data is not distorted by asking whether the factory's sold output in the last 2 weeks. Yeah, Richard.
But you're adjusting for the participation rate.
Yeah.
Not the other.
Yeah, that's right. This is free of the distortions that are involved in generating the participation rate. It's much more realistic. Now you look at it and notice that the employment rate peaked at 64.5% in 2000. It's now down at 60%. Now that again, that's partly affected. This particular data is the employment rate for the population between 15 and 64. But there's also another series between 25 and 54. Now 16 to 22, you can be expected to be at university. and 55 on, you might be retiring. 25 to 55, no. 25 to 54, you've probably finished university, and very few of you are going to have to be able to retire yet. Now, when you look at that, this is an important political aside here, that rate isn't quite as extreme as this rate. This is reflecting what's happened with technology over time. But that rate peaked at, I think, about 82% in 2000 and is 78% now. And in terms of the number of, you again adjust for demographics and look at the change in the demographic makeup of America as well. There are 2 million less people aged 25 to 54 who have a job now that had a job in 2007. I think they voted Trump. Okay? And when you look from 2000, it's actually 4 million people. So that's a bit of a political aside here, but that's why I tend to now use the employment rate, because I'm just sick of the distortions, particularly applying American data of the unemployment rate. So that's your second component I'm trying to look at. Now the third component is energy consumption per head, and that looks crazy. Again, this is data from the originally from the Department of Energy in America, but you can see the data source I've got there. I think I haven't actually made it clickable here, but that's the Europa database, which is part of the European Union, and this is looking at energy consumption per head in the United States. You can find similar series for about 40 countries. Notice it peaked way back after this time of the second oil crisis. Huge plunge, reached a peak in 2000, now come down quite substantially. I got quite a surprise when I saw the data looking like that. I would have thought there would have been more of a trend of rising over time, but energy per consumption per head's actually fallen. Now, a lot of that would reflect an increase in energy efficiency, okay? But it's also going to affect aspects of income distribution as well. The rich don't need, even though Donald Trump flies around in a 747, okay, that isn't consuming as much. If you had distributed all the money he earns or has to amongst thousands and thousands of people, the amount of energy the cars those people would drive would far outweigh the energy needed to fly the Trump-mobile around the planet, around the country. So that's the data I'm now trying to fit to that equation. And of course, there's going to be a correlation between GDP per capita and the employment rate. That'll turn up. We know that's going to be there. But if I take the data and I then fit it into that equation, I go from a correlation of 0.59 between GDP per head and employment, and 0.62 between GDP per head and energy per head, to 0.78 when I include that equation. So the function, if I use alpha equal to 0.7, and now alpha doesn't mean anything about income distribution. Okay? It's a scaling factor. I've still got to work out what it actually is in the equation, but it's no longer an income distribution statement. I'm going well over time here, I just realised, but I'll finish this point before I go on to the next one in a moment after a break. So that's the function with alpha equal to with an energy only gives me a correlation of 0.59. So GDP per head to energy per head, correlation 0.59. GDP per head to employment, the employment rate, 0.62. Putting the function in there, I get 0.79, a substantial increase in the accuracy of the correlation. So to me, that implies empirically this equation's got legs. Okay. So I can also start looking at what actually determines these things over time. And there's going to be, we now look at social dynamics as well as technological dynamics turning up and how we produce output. So what we have here is energy turning up over here, innovation in terms of the amount of energy per machine that we actually can use at a point in time, and the class struggle over how much of this goes to workers versus how much goes to capitalists. So we should be able to make a link between this equation as well and also the entropy and waste elements, because I've got in here the fact that we're wasting some of that energy. So I think it's possible to get an energy-aware theory of production and then to incorporate that into economic theory. Now, you can't do it with the Neoclassicals because since they've tied their theory of production into their theory of distribution, this shows that can't be done. Okay? So that's gone. And that's an essential link for the neoclassical theory. If they included the stuff properly, they would no longer be neoclassical, which would be a great idea. But whether they'll do it, I'll have to wait and see how they react to the paper when it finally comes out. Inputs don't receive their marginal product. They consume far more than that because they're sharing, labour and capital are sharing in the output generated by energy harnessed by machines, fundamentally. And you also say that energy harnessed by machinery is by far the major source of useful work. Labour theory of value is also wrong. So the payments going to the owner of the energy, which is largely capital, but labour and capital fight over the distribution of that. And there's a far harder than the marginal product. So bang, no longer neoclassical theory, because that meritocratic argument about distribution is an essential part of how they think about the real world. Post-Keynesians, on the other hand, can cope, and at that point I'll take a break, because I know I've bashed you guys around the head a fair bit here. Let's take about a 5 or 10 minute break, and I'll finish up with a bit of a lead into next week's lecture on the philosophy behind all this. Having said the neoclassicals, if they properly incorporated this understanding, they would no longer be neoclassical. So can the post-Keynesians incorporate it and still be post-Keynesians? My answer is yes, but they should need a theory of value. Now, if you look at, as mentioned, that Harcourt and Hamuda paper earlier, that really said that you just use whatever works, so you grab whatever model until it works. And if you look at the neoclassicals, their attitude was, well, you have to work from some shared foundation to build an overall theory of economics. And even though I think they used the wrong shared foundation, I'm on the neoclassical side to say you should have a foundation from which you derive a starting point. So the post-Keynesians, by saying it's horses for courses, grab whatever model you like, that really makes it difficult to explain why their critiques of neoclassical. And this is what the reply that Roger Backhouse made to Harcourt and Hamuda was precisely that point. If you're in for horses for courses, why will you never ride a neoclassical horse? So there is some sort of shared philosophy amongst post-Keynesians, even though they don't acknowledge it. And there is another developed alternative. I never had a chance to finish this paper. There's a long story behind it. But if you look into some of the philosophical foundations that influenced Keynes himself and also the early post-Keynesians, it came from what's called organicism, which came out of work from which I've forgotten the original author. As long as I look at this. But if you look at the papers I've cited here, there was a philosophy coming from Whitehouse, I think, the philosopher Whitehouse, that the characteristics of any particular entity are largely the outcome of its relationship with other entities. In other words, rather than defining you in isolation Robinson Crusoe style, which is what neoclassicals try to do, your existence, your role in society depends upon your relationship with others in society. Okay. So organicism rather than reductionism was the essential invite there. And if you have reductionism, you can't see that. If you say you can explain everything using Robinson Crusoe, then you've left out the relationship that Robinson Crusoe has with other individuals on his island, because there are no other individuals on the island. Okay. So you have to analyse the system by looking at the relationship the entities have with each other. But then you get the problem, how do you handle it? Because that means everything depends on everything else. Now, the neoclassical answer is let's go for ceteris paribus, Whitehead, I think Amy Whitehouse rather than Whitehead. Whitehead said that the relationships we have with other entities form a nested hierarchy. And to explain what that means, you have, I've jumped too quickly to go to Marx, so I'll talk about the organicism thing a bit next week. But the idea is that if you think about our relationships with other entities, the relationship that an entrepreneur has with workers, okay, is not going to be affected by the entrepreneur evolving into some other life form. Okay? So the evolutionary change we're undergoing is slower than the social change we undergo, and therefore you can ignore evolutionary issues in terms of us evolving into a different species while you talk about worker-capitalist relationships, that sort of thing. So talking about a nested hierarchy was the element that you find in Whitehead that Keynes accepted. And what I'll argue next week is that that's also what exists in Marx. Marx had a concept of nested hierarchies, or an organicism, which was ignored because of this obsession that Marx had as well, saying that labour is the source of all value. Because when you look again at that equation I've taken you through, the energy that a machine exploits is far greater than the energy an unskilled labourer can provide. So in terms of the amount of useful work we can do, by far the vast majority of that useful work comes from what machines do. We then harness it to be able to exploit the energy. We fight over the sharing of that between workers and capitalists, but fundamentally it's the efficiency, the amount of energy that machines can handle that is the real source of our wealth. Now, that would, if Marx only had the labour theory of value, then I'd be throwing Marx out the window, because the argument that labour is the source of all value is incompatible with the laws of thermodynamics, as I've shown you in today's lecture. But Marx had a dialectical theory of value as well. And this is compatible with the organicism that the post-Keynesians have. Again, if I was giving an HET course, I'd cover much more detail on the post-Keynesian one. This basic idea is the organicism idea that Whitehead had, was that the wider context of all human beings is more stable than the narrower one that some of us are capitalists and others are workers. Okay? So you can ignore evolution while you're working about the nature of capitalism. Ignore evolution of humans at that time. So you take the wider context as given, you work with the narrower context. And then when you've expanded that sufficiently, then you take on the wider context again. So the fact that you've got this nested hierarchy means you can start from a core and work out. And so the evolution of the entrepreneurial function over the next 5 years, you can ignore over that time how much humanity will evolve over the same time period, that sort of thing. That's the idea of a nested hierarchy. Now, dialectics is Marx's underlying philosophy. And this is an incredibly contentious field. As I said, there are some Marxist economists. John King, who was a leading Marxist, he's now more of a historian of economic thought, but John rejected the argument that dialectic was essential. John actually marked my master's thesis very, very positively. They're rejecting my arguments, which I'll be giving you next week. I see this dialectics as essential to understanding Marx. If you ignore it, you don't understand Marx. And most Marxists have ignored that philosophy completely. And if I mention dialectics, can anybody give me a phrase that encapsulates what is meant by dialectics? Pardon?
You create something in its solution.
Something in its opposite, yeah. But there's a particular phrase. I had it on the screen a moment ago. I hope none of you were looking fast enough. Thesis, antithesis, synthesis. It's incredibly hard to say, and it's not Marx. This is the remarkable thing. When I first read Marx, I led a student revolt at Sydney University against the teaching of economics there in 19... Hey, what's going on there? It's actually swapped around the wrong way around. Wasn't seeing you've got my notes over this side here. I've swapped the view. That's readable enough, isn't it? Okay, I'm recording the screen here, so I'll leave it that way. There was a student revolt over the teaching of economics in Sydney University in 1973. I was one of the 3 leaders of that revolt. And there's 50 or 60 students involved. It was a hell of a lot of fun. Get me slightly ripped one of these days and I'll tell you the full story. But we had after the whole thing, we had a Marx reading group. And I was very sceptical about the argument, and this you can see this turning up in what I'm doing now, very sceptical about the argument that I knew Marx made, that machines contributed nothing to value. They only contributed what they lost in depreciation. As it happened, 1973 was a huge, the Trumpian word again, a huge building boom around the world, but particularly in Sydney. There were cranes all over the skyline. You walked around the campus of Sydney University, which is on a rise at the end of the Sydney CBD. You just see cranes everywhere. I remember saying to a friend of mine, I simply can't swallow that those machines are adding no value. Couldn't cope with it. So I wanted a really good explanation from Marx about why it was that machines didn't create value. We did this. What a way to waste a Sydney summer. We spent several weeks doing a reading group, all reading Das Kapital for the first time, and discussing it in the philosophy rooms at Sydney University in the middle of a heat wave. And I read it, and I thought that I couldn't see anything about thesis, antithesis, synthesis. There's nothing that I could put in those terms in Marx. And it turned out later when I did my master's thesis that was actually the approach to the dialectic that a guy called Fichte had. And that's German. I'm mispronouncing that as well. Not Marx. I've linked there to the best book on Marx's actual philosophy, a guy called Wilde, called Marx in Contradiction. So you're going to get a really good philosophical and historical explanation of Marx's real approach, real dialectics. Read Wilde. Don't accept people who've put this thesis antithesis, synthesis stuff because they got it wrong. They're not Marx's logic at all. But when you take a look at it, you find that Marx has got this idea of organicism and transcendentalism, and he never explicitly set it out. Never explicitly say, this is my philosophy. But if you read enough of his work, you'll find these concepts turning up all the time, and particularly one called the Grundrisse, or otherwise known as the rough draft of capital. So when you apply it, I think it gives you an integrated foundation for thinking about economics. It's consistent with the thermodynamics I've shown you beforehand. Okay? Not based upon it, but it's consistent with it. And I've double-proved myself there, the Grundrisse, and I'll talk about that next week. So I've bashed your brains out enough for one day. Let's have a bit of a chat. I'll just save that.